So in this video, we're finally going to kind of get into the meat of this unit and really talking about the new things that we're going to be learning, which is the chemistry that occurs in solutions and how solutions behave. So in chemistry, a solution is a homogeneous mixture. So really these two terms are essentially interchangeable. And a homogeneous mixture is just a mixture of two or more components that is uniform throughout. So that means that if we look at it, it looks like one thing. It looks like everything is the same throughout, but at the molecular level, there's actually more than one chemical compound in there. So in a solution, we have two primary components that we refer to as the solute and the solvent. So our solvent is whatever component of our solution is present in the greatest quantity. And then our solutes are whatever components are present in lesser quantities. So we can have more than one solute. We can dissolve more than one thing in a solution, but we can only have one solvent. Usually it's whatever there is the most of, is what we refer to as the solvent. So for example, in something like your morning coffee, if you're a coffee drinker, you may dissolve sugar in your coffee, you may put cream in your coffee, and coffee itself is actually already a solution that you brew coffee with water. Water is the solvent. When you pass the water through your coffee grounds, the water is actually dissolving stuff out of the ground up coffee beans. That is what imparts the flavor and the caffeination into your morning beverage. So even just coffee by itself without cream and sugar is already a solution where water is the solvent and you have caffeine dissolved, you have all sorts of different flavor compounds dissolved, and all of those different things are your solutes. Sugar, if you add it, would also be a solute. Cream is again already a solution before you even add it. Cream is mostly water with fat and protein and sugars and stuff dissolved as the solutes in it. So solutions are really everywhere in life. Basically, like any liquid that you touch is probably a solution for the most part. We don't encounter a lot of pure compounds as liquids in our daily life. Any cleaning products you have are solutions. Your shampoo is a solution. And solutions don't have to be liquids either. We usually think of them primarily as liquids, but we'll talk a little bit about solid solutions towards the end of the unit. And solutions can be gases as well. The best example, of course, being air, where nitrogen is the solvent. Air is mostly nitrogen, and then the solutes are oxygen, carbon dioxide, and all of the other gases that are present in small quantities in the air that we breathe. So we will be focusing mostly on solutions where water is the solvent in this class. So we have a special name for that. These are known as aqueous solutions. So an aqueous solution is just a solution where water is the solvent. So another important thing to recognize that's going to have implications for the chemistry down the road is that when an ionic compound dissolves in water, and this is mostly what we're focusing on in this unit, specifically ionic compounds dissolving in water. So when that happens, when an ionic compound dissolves, and this is actually true when an ionic compound dissolves in any polar solvent, so when an ionic compound dissolves, the ions actually split apart. So what I mean by that is that for something like ordinary table salt, NaCl, when we have that in the solid state in our salt shaker, all of our ions are connected by ionic bonds. So we have something that looks more or less like this, that we have this lattice type structure alternating between sodium ions and fluoride ions. And when we dissolve that, those ions come apart. Our ionic bonds actually break. So when we dissolve this into a beaker of water, we don't have these connected ions that are all touching anymore. They spread out throughout the whole container and detach from one another. So our ionic bonds are broken and our ions spread out. And this has an effect on how things react in solutions. This is a really important part of why things react the way they do when they're dissolved, and why they react differently when they're dissolved compared to when they're in the solid state in many cases. So this is something to always kind of keep in the back of your mind, and we'll come back to over and over again, this idea that the ions are split up and why that's important. So we also need to recognize that not all solutes will dissolve in all solvents. So when something is able to dissolve, we refer to that as soluble. And this idea of solubility is a little bit qualitative. It's not super precise whether something is soluble or insoluble. It's not really a yes or no question. It's a spectrum, it's a continuum. So when we say something is soluble, we don't just mean, yes, you can dissolve as much as you want. What we really mean is that you can dissolve a significant amount. And what significant is kind of wishy-washy. There's not one set definition of significant. It is context dependent. Usually how I like to tell people to think about it is, if I put a teaspoon of the stuff of whatever solute we're talking about into a cup of water, would it dissolve? If yes, it's soluble. If no, not really, it's insoluble. So that's kind of a good way to envision it in your mind. But again, it is context dependent. So sometimes you'll see, if you look at multiple references, you may see a particular substance listed as soluble in one and insoluble in another, and it just kind of means it's on the fence. Or sometimes you'll see something listed as slightly soluble, which is, you know, sort of that in-between gray area. So insoluble means we cannot dissolve a significant amount. So if I put that same teaspoon of solute into a cup of solvent, it would probably look like nothing happened. It would seem like nothing dissolved. That may not be the case. You might actually be dissolving a small amount, but if it's not a noticeable amount, it's not a significant amount, then we consider it insoluble. Even if a tiny bit does dissolve, we still say it's insoluble. for the purposes of chemistry, the amount that dissolves is too small to usually be bothered with. So this idea of solubility, that some things are soluble and some things are insoluble, comes into play in double replacement reactions. If in a double replacement reaction, one of your products is not soluble in water, it can't stay dissolved, which means it's going to turn into a solid as it's produced. So if a product forms that is not soluble, it becomes a solid. And this solid is what we call a precipitate. So our solid product is referred to as a precipitate, and the reaction is known as a precipitation reaction. If a precipitate forms. So what we're looking for to detect if a precipitate forms, when I say that it turns solid, people have this vision in their mind of you get one big chunk of solid, or it looks like salt in a salt shaker or sugar in your pantry. But that's not really the case because it's forming all throughout the solution and it's forming so quickly. The particles you get are very, very, very tiny, so it's usually more of a powder, which means that the solution pretty much just turns opaque or gets cloudy. That when something is completely dissolved, the solution is crystal clear. You know that if you dissolve just some sugar in plain water, when you're done, it still looks like water. It's crystal clear. But if a precipitate forms, that solution gets cloudy, is how we know visually in the lab that a precipitate has formed, that something insoluble has been produced by this reaction. So our solution becomes cloudy or opaque. So if no precipitate forms, our solution stays crystal clear. And what this tells us, if we do a reaction and it stays clear, nothing really happens, then that means that all of our products are soluble, that they were all able to stay dissolved. And this really means that no reaction actually happened. And we'll talk more about this concept a little bit later. So now I just want to really quickly show you a few examples of what double replacement reactions look like with and without a precipitate. So the first combination I'm going to do is calcium nitrate with sodium chloride. So these are already aqueous solutions. So this is sodium chloride dissolved in water. This is calcium nitrate dissolved in water. So if I combine a little bit of each of these, we should see a whole lot of nothing happening there. And that is because the products of this reaction are all soluble in water, so everything stays dissolved, which means that essentially nothing really happened. So we can contrast that to my next combination, which is the same calcium nitrate dissolved in water, but now reacting it with sodium carbonate dissolved in water. So here's here's my calcium nitrate. And when I add sodium carbonate to that, we should see something different happen. So in this case, you can see that my solution turns white, and it is very, very cloudy. It is no longer see-through. So if we compare these two test tubes, you can tell that you can see through the one on the right, which has all soluble products, but you cannot see through the one on the left, in which one of the products we produced was not soluble in water. So that cloudiness you're seeing is the solid that was formed, is the precipitate.